All right. What we talked about last time is that there are 4 different centers of a triangle, and each one can be thought of as having an if-then scenario. For instance, here's the circumcenter. If I put together certain segments, special segments, then it produces an unusual effect. Do you remember what 3 segments produce the circumcenter?
Perpendicular bisector.
Very good. And if I take my 3 perpendicular bisectors and I use them to find the circumcenter, what's the interesting feature or the cool thing about it?
It's the very center.
Well, that's not going to be enough words or enough specificity in the words because they're all centers of the triangle. Good. So the deal is it produces something that draws a circle around the triangle so that all 3 vertices are the same distance from that circumcenter. In other words, the circumcenter is always equidistant from the vertices of the triangle. Now, again, I like to think about this as an if-then. So in other words, if perpendicular bisectors, then this picture, right? They're the same distance away. So first of all, let's look at the if part, the hypothesis. List the perpendicular bisectors. What would be one of them? Good. PE is a perpendicular bisector. You know that because it shows that it's a bisector since those segments are the same and it's perpendicular. What's another one? Yeah. PF is good.
PD.
And PD. And all 3 of those perpendicular bisectors meet at a single point. It's called a point of concurrency in general. This particular version is called the circumcenter. So what is it that's the circumcenter in this picture? Point P, good. And you'll remember that we use a capital letter to describe a single point. List all congruent segments. Now, I know that these segments are shown to be congruent, so they're congruent also. But let's not list the ones that are totally congruent by given, effectively. Instead, let's use the hypothesis and conclusion idea. The hypothesis said, if I produce these perpendicular bisectors, then what's true? It's equidistant to the vertices. So in other words, PA is equal to PB, which is equal to PC. And in fact, it says congruent segments. So I guess I better change those to segments and make it congruent so that we match what they asked for. Any questions? Let's do a little application of it. Question? What is the circle equidistant part? Remember when we used a compass to make a circle? And what makes it unique, of course, and doable, is that I get a very locked in, fixed in radius. And so if I were to put my compass on the circumcenter and trace a circle, what I'd find is that that same length goes from that point to any of the 3 vertices. Let me try one more way of doing that. We did this a little bit last class. So if I take 3 points and I turn them into a triangle, and I do a circumcenter, this particular tool is cool because it allows me to create first the midpoint of any line just by clicking on it. And then I can produce a perpendicular line through that by telling it what line and through what point. So if I do that to all three sides, they're going to meet at some point. And what's cool about this is no matter where I do it, because I'm constructing this effectively, that point of intersection there is going to be consistent. In other words, no matter how I move this triangle, that point of intersection is going to be all three of those lines. And so now, if I were to take that point, let's see, I guess I need a point there. I take that point and go from that point to A, saying that G to A is the same distance as G to C is the same distance as G to B. In other words, I can draw that circle. And as I drag this around, I mean, this is a weird looking center of the circle, of the triangle, isn't it? Because here's the triangle ABC, and I'm saying that G is the center of it. That doesn't feel like a center, does it? Because it's not even in the triangle. But if this triangle is in fact acute, then the center will be a place where it's the same distance to all three vertices. If it's a right triangle, it turns out that it'll be on the hypotenuse, right at the midpoint. And if it's an obtuse triangle, it'll actually be outside of the triangle. Does that answer your question, Jonah? Okay. So let's apply it here. Here's a picture. And we're told that this is the circumcenter. And that means if these are perpendicular bisectors, then the distances from that point to the corners will be the same. So if 21 is the distance from Z to V, what else do I know as 21? Very good. Those are all going to be 21. So TU is going to, nope. VY, nope. UZ is going to be 21. And if I'm looking for TU, what do I know about this? Given that it is a circumcenter, my hypothesis says this line here must be right angle because it's perpendicular. And what's it doing to this TU? Bisecting it. So if this part's 19, isn't this part also 19? Therefore, TU would be 19 plus 19 is 38. What about VY? Good. If 34 is the whole length, and this is in fact a perpendicular bisector, as we know it is, this would have to be 17, and so would this, so that together they make up the whole and they're equal. What about WV? If I knew WV, and we don't know it yet, what would I know about TV? It's just double, right? So the question is, how do I find TV? Well, see this triangle? What kind of triangle is that? Good. Because these are perpendicular bisectors, I know that that's a right angle. And one of the theorems that we honestly haven't learned yet, and I don't love that they bring it up here, but they do, so okay, is if I have a right triangle with a side length A, a side length B, and a hypotenuse of C, then Pythagorean theorem applies. A squared plus B squared equals C squared, where C is the hypotenuse, the one opposite the right angle. So in this case, do we know A? 15 squared. Do we know B? No, that's what we're looking for. Do we know C? 21 squared. Then I'll square this. So 15 times 15 is 225 plus WV squared. 21 times 21 is 441. So WV squared subtracts 225 from both. What is that, 216? 4 minus 225. Yeah, 216. And later we'll learn about what to do in terms of how we simplify these. We're not doing that yet. We're just going to say that WV is equal to square root of 216. Any questions on that? Yeah, Theo?
Are we gonna use total for
Which part scares you? The Pythagorean theorem part?
just curious?
Okay, we'll spend some time with it. Assuming this is the length of WV, how big is TV? Twice that. So I'm going to write 2 on the outside of this times the square root of 216. It's twice as big. Okay. So as part of your homework tonight, you'll do number 2, which is a very, very similar problem. Let's go on to our second center, an incenter. The incenter is formed by what? Which segments make the incenter? Angle bisectors. And that's the if, right? If you connect the 3 angle bisectors in a triangle, producing the incenter, then what's special about it? Good. Equidistant from the 3 sides. So in other words, I could draw a circle in the center of this triangle such that it's exactly the same distance to each side. And when I measure to a side length from a point to a side, I always use the perpendicular distance because that's the shortest path. So the incenter is always equidistant from the sides of the triangle. So now let's list the angle bisectors. Here's an angle. It's been split evenly. AP. Okay, CP. And BP. And again, all 3 are reaching point P, which tells us the name of the incenter is P. Now we're going to list all the congruent segments. And again, if there were marks shown, I wouldn't want to list those. I'm looking for the then. As a result of this being an incenter, what's now congruent? Good. DP, EP, and FP, because those are all measurements to the side length. Perpendicular going the shortest distance to the sides. So DP is congruent to EP is congruent to FP. So what can we do with that fact? Well, here they're telling us that P is the incenter. Okay, I know that's formed by angle bisectors. Therefore, these vertices, 2 point P, must be congruent, right? They're angle bisectors. They're broken up into congruent angles. And since it's the same distance to each side, this length of 8 is the same as this and is the same as this. So they're asking about NP. That one's a slam dunk. I know that one's 8. They don't ask for PO, unfortunately, so I can't put that one in. They're asking about NK. See if you can get that. How could I find the length of NK? Oops.
That's 17.
It is 17. How'd you get that, Harris?
Yes.
Guess? No, I think it's an educated guess. See these 2 triangles I've colored pink? What do you know about them? They share this angle. They share a right angle that's congruent. What's the third piece of information we know is congruent? You could do PK is reflexive, or you could do these 8s. Either way, angle side says these 2 triangles are congruent. If they're congruent, then OK is the same as NK by good CP CTC, exactly right. So we know NK is 17. and PK. So in other words, I'm looking at this triangle that I know is a right triangle. I know this is 8 and this is 17, and I'm looking for that. How could I do that?
A squared plus B squared plus C.
Yeah, it's a Pythagorean theorem. This applies because it's a right triangle. So I'd say 8 squared. Which one's going to go on its own over here? X, because that's the slanted one. That's the one opposite the right angle called the hypotenuse. So 64 plus, what is that, 269? And so 320, 333. Is that right?
Yeah.
289, thank you. So 353 equals x squared, which means 353 with a square root symbol is equal to x, which we said was pk. And again, later we'll learn how to simplify these or approximate them, but for now I'm asking you to write it in an unsimplified form. Okay, how would I find LO?
Oh, Pythagorean theorem.
Pythagorean theorem again. I'd say 8 squared plus LO squared equals 13 squared. 64 plus LO squared equals 169. So LO squared is 105, which means LO equals square root of 105. Any questions? Let's go to side 2. What is a median? It's a segment that joins what to what?
Vertex and midpoint.
Good. Vertex to the midpoint of the opposite side. These marks show that it's the midpoint. This is going through the vertex. If I take the 3 medians of a triangle, they intersect at a point called the centroid. So what would be the medians in this picture? DC, good. From a midpoint all the way to the opposite vertex. AE, good. Good. And this time, the endpoints aren't the centroid. What is the centroid? P. It's still the point of intersection. It's just not the endpoint of the segments. Now, one piece of information that you know about this is that if this is a median and this is a median, that identifies P as a centroid already. If I come out of B through that same centroid, what has to be true about this side? It's got to be bisected, right? AF is equal to FC. But here's something you probably didn't know. When I look at the centroid, it exactly splits the medians into parts, not equal parts, but parts where this is X and this is 2X. So for example, if EP were 10 units long, how big would AP be? 20. And if you knew that PC were 50 degrees or 50 units, how long would DP be? Good, 25. So in other words, what we learn is that DP is equal to 1/2 of PC. That's one of the examples. We can also say that EP is equal to 1/3 of the whole length EA. And then we could say that BP, in other words, from a vertex to this centroid, is going to be 2/3 of the whole length. Any one of those relationships could be useful to you. Let's see if they're useful now. Let's do number 2. If Z is the centroid of triangle TUV and TZ is equal to 60, what do you know? ZY is going to be half of that. So ZY is going to be 30. It also tells us that XZ is 28.
56.
For what?
C.
Good. 56. What about XV? We'll get there in a second. What about XV? Good. We're adding these two together, right? So 28 plus 56 equals 84. And then ZU, let's see, they gave us WZ is equal to 25. So how long is ZU? 50. What about TY? 90. Easy? Any questions? Okay, last one of these. An altitude is a segment that joins the what to the what? Yeah, good. Vertex, and then it goes down in such a way that it's perpendicular to the opposite side. Perpendicular. And you guys may remember from, I would guess, 5th grade or so, when you did area of triangles, that sometimes that altitude of the triangle can be right what you expect it to be. What happens when you've got an obtuse triangle and you're trying to find the altitude to this?
It's not exact.
It's outside of it. I got to like extend this leg to find where it is. And I go down that height. So if I were finding the area of this, I'd actually only do this part of the base times this height divided by 2. What if it's a right triangle? Yeah, it's just this side length over here would be the altitude.
Can you look like you up to kind of over and then?
Yeah.
So then the right angle is on the outside of the tablet.
Like this? It could. And if you knew this side length, then you could use this to find the area.
So why didn't you just do that originally?
Well, what if you didn't have that? Right? Like what if you only knew this base and this height? Then you'd need to use those to find the area of this triangle. But you're right. If you did know those pieces, you could use that as well. Say again. Partially inside the triangle? No, it's either going to be inside, outside, or on. Do you have a scenario you think it would be partially? In here? But if I go up to the height, okay, but that wouldn't be the altitude of the triangle. That would be forgetting about this part of the triangle. So I couldn't use that. Do you want to bring it to me and let's see. Oh, I see what you're saying. Okay. So in other words, if this thing were to be like carried over as a continuation of what height it is, and then you measure that. In other words, this is parallel to that. That's true. You can measure the height there. Maybe that's easier to see that it's this times this. Okay, and if I take the 3 altitudes of a triangle and they intersect at a single point, it's called an orthocenter. And you'll see in this picture that you're going to create the altitudes and you'll see what the name of it is. There's nothing fun about the Orthocenter. It just doesn't have any of the cool features that these other ones do. So we won't go into that. Right, on this side, you're going to be looking at these pictures and you're going to be not only determining from the picture whether it's an incenter, a circumcenter, a centroid, or an orthocenter, but also conveying what's special about it. So for instance, what's this one? That's an incenter because it's formed by 3 angle bisectors. And what's special about it? Good. So you could choose to put the circle on the inside to show that it's equidistant. Or you could just say, I know that this length is the same as this length is the same as this length. Either one of those would describe what you're saying, or you could use words, equidistant from all 3 sides. Okay, you've got the rest of the period to work on this. If you have other things you need to work on, or you want to work on that quiz request from this morning, we can do that too.